Check.
Yes, what's up?
It's time for things you thought you knew.
Or if we actually said it from my perspective, stuff you about to learn.
Stuff you never knew. Is that what
Yeah,
you're
because
saying?
you know damn well you didn't know it before.
I have to address something that I think we've seen in the news. You know, every 6 months goes by, and then you see a headline, astrophysicists have to rethink the Big Bang, or Big Bang is debunked, or did you see any of these at any time?
Oh, my God. Recently, the James Webb Space Telescope, supposedly, the headline is, did the James Webb Telescope make scientists think the Big Bang? Or has the James Webb Telescope debunked the Big Bang?
Yeah, it makes excellent clickbait.
Yeah.
There it is. It's clickbait headline. So let me just explain a few things that's going on here, okay? On the frontier of scientific research, it is a bloody place, all right? Ideas are slayed.
2 scientists enter. 1 scientist leaves.
It's the octagon.
Welcome to Science Dome.
On the frontier, ideas are contested daily.
Right.
And most ideas turn out to be wrong. All right. So what you are as a scientist working on the frontier, you're in this idea factory. That's what you are. And the successful idea is not the one that's argued most strenuously or argued by the most articulate.
Yeah, that's called politics.
It's called politics. Exactly. It's not. It has nothing to do with either of those. It has to do with evidence. All right, which idea is supported by evidence? So typically what happens is you contest your ideas, and here's where you have to be convincing. You have to say, I think my idea is better than your idea, and here's a way to test it.
Right.
So I have an idea. So if you don't like me, the way you show it is you design an experiment to show I'm wrong.
Ooh,
okay.
Ooh, that's some cutthroat, nasty stuff.
That's some
right there.
It's some nasty.
Ooh,
all right.
That's some Real Housewives stuff.
Real Housewives.
Let me tell you something, Phaedra. Your hypothesis is trash. Trash.
So scientists contest their ideas. So you don't like me, and you're going to show me that I'm wrong, and so you go home and you invent an experiment. You invent an experiment to test my idea with the objective of showing that I'm wrong. And it turns out, hey, wait a minute, I'm getting what the dude says.
Right.
You got to publish that.
I'm picking
and
up
then
what
someone
you're
else
putting
performs another kind of experiment aimed at testing the same hypothesis. And they get kind of the same result. And then someone from a different country with a different wall current, 240 volts maybe, and they plug their stuff in, and they're getting the same result. When you have repeated experiments verifying an idea, we have a new objective truth that has emerged in those sciences. And what I'm telling you is that the Big Bang theory, by the way, if you type that into Google, you get the TV show. My personal jury is still out on whether that's a good or bad thing. It doesn't mean like science is so popular, it's a TV show, and that's the first thing you hit, because you got to get through that. Then there's the Big Bang is a K-pop group. You got to get through that. Then you get to the origin of the universe, okay, in the Google search. Just thought I'd point that out to you.
Well, it's good to know that we Google in order of importance.
There it is. Just saying.
Wow.
All right. So here's the point. The tenets of the Big Bang, that the universe started out small, hot, dense, where matter and energy were a primordial soup, where the forces of nature had merged. All of that is thoroughly supported by observations of this universe. Thoroughly supported. Okay? Now, there's some things that, well, did this really cause that? Or might it be something that we don't know about yet? And who ordered up the dark matter? We don't know where that came from. And where's this expansion? We don't know where that came from, but we can describe it and we can measure it. Here's the point. If tomorrow you have a new idea about how the universe works, it's going to enclose everything we've been talking about up to that moment that has been experimentally and observationally verified. You can enclose it in something deeper. Okay, you can say, oh, wait, I have an idea. Our universe is just one in a multiverse. Right. Fine, okay? But our universe would have started with a Big Bang, okay? Right. And our universe would have expanded from a dense, hot state, and it's been cooling ever since. That's observed, and that's real, and that's not going away. That's my point. So what you have are journalists trying to make clickbait. And if there's some little thing in the early universe that is still on the frontier, still being contested in the octagon, in the fight dome, and some new idea is emerging over another idea, people say, "Oh, Big Bang is in trouble. Scientists go back to the drawing." But Big Bang is not in trouble.
Right.
I'm just saying, it's not in trouble. It is a whole thing that could conceivably fit in a deeper, bigger idea. But it's not going to be swapped out tomorrow. We're not going to find out tomorrow, gee, the early universe was cold instead of hot. That is not going to happen. That's not how science works.
So if you're going to come up with something new, you're not coming up with something that will change the old. All you have to
the old that has been experimentally verified.
That's done.
Right. If you're going to come up with something new about the Earth and the Sun, it's not going to be, well, it's really Earth is stationary and the sun moves around the Earth and the sun is cold and Earth is hot and Earth is what's illuminating the moon. That is not going to happen.
Right.
Okay? You can't just pull an idea out of your orifice and ignore experimental verification of what's going on.
Right. So you might come up with the Big Fang, but you're not changing the Big Bang. Well, what's the Big Bang?
I get a C plus on that one.
Yeah, it's what came before the Big Bang. We call it the Big Fang.
The Big Fang. Okay, that's a B plus. If that's what's your thing? Yeah, that's before the Big Bang.
Yeah, it was before the Big Bang.
So, and by the way, when we think of Einsteinian physics, so it's relativity, which completely usurped Newtonian gravity and Newtonian motion. All right? What we call the era of classical physics, which led right up to the late 1800s, Newton's ideas reigned supreme. All right? And he told you what gravity did, what motion did, and acceleration in a pre-existing space, and it was working. Okay? It was working. And then people said, well, wait a minute. The orbit of Mercury is not really following Newton's laws. And we said, oh, we got this. We know we got this. There's another planet you can't see that's tugging on it. We even had a name for that planet. It was called Vulcan. Okay? Huh? A hypothetical planet tugging on Mercury so that we didn't have to throw out Newton's laws. All right? So that was invoked we just pulled that out of our ass, right? Said, there it is. We'll find it one day. Einstein comes along with a special theory of relativity, and that is general theory of relativity. And what we find is that at high gravity, like near the sun, and at high gravity and high speeds, Newton's laws completely fail. You cannot use them at all. So did we throw away Newton? No, we didn't. You know why? Because if you take Einstein's equations and plug in low speeds and low gravity, they become Newton's equations. Yes. So Einstein basically enclosed Newton's ideas as a special low speed, low gravity case of a much larger, deeper understanding of the universe.
That is fantastic.
It is beautiful. Yeah. It is. And by the way, Newton's gravity and Newton's motion were just fine for the Apollo project.
Right.
We got to the moon and back without any Einstein relativity at all. Okay? So it's only if you really up the stakes in your gravity. There's no way to understand black holes, really, or even the Big Bang itself, with just Newtonian physics. Point is, new physics does not undo experimentally verified physics. Right. That's the whole point of experimental verification. That's all.
Look at that.
And so the Big Bang is just fine. You want to do something else with it? Take it body and soul and stick it in some other theory you have. But you can't undo what the experiments and observations have shown. And that is an explainer for you.
There you go. Wow, that is good. Take that, Big Bang deniers. Take that.
All right, Chuck, we got to take a break. But when we come back, more things you thought you knew on StarTalk. There's a feature of the James Webb Space Telescope that I haven't seen talked about much. People only just think of it as some next big telescope that's out there in space bringing us badass images. But there's certain engineering scientific features that are unique with it that I think are worth calling out.
Okay. That sounds good.
Right. If you can hang with me on this, all right. Allow me to remind us that unlike Hubble, which orbited Earth 360 miles up, this thing is parked 1 million miles away in the opposite direction of the sun from the Earth.
It's pretty wild.
Okay, yeah, and so I say parked. We're all it and the Earth are orbiting the sun together, and so basically, if you look back in the Earth direction, the sun will always be there.
So it's using the Earth as sunblock.
Well, it has some motion where it is, okay, but it's not going to drift away from that location, even though there's some movement within the location. The point is, occasionally Earth will block the sun, right. But the value of this is you always know which way the sun is,
right,
at all times, okay? Gotcha. It's behind you, okay?
Right.
All right? I'm looking out to space.
The only way to take good pictures. And know what they say? Like,
good one. Yeah, it's true.
Get the sun behind you.
That's right. That's right. So that everyone is squinting as they look in the camera.
Exactly. Right.
So if you're going to take a picture of something that's dim, you either have to illuminate it yourself, which we really can't do for the early universe. That doesn't work. Or you can take a long exposure to allow the light to accumulate. But while you're taking that long exposure, you can't jiggle the camera. It has to be perfectly stationary. Still. So Chuck, just to repeat, we can't take a flash picture of the outer universe. So we have to open the exposure for a long time. Okay, so now watch. Different bands of the electromagnetic spectrum tell us different things about the universe. All right, so if you're going to do that, you need telescopes that specialize in the chosen band. And by the way, we didn't even know light came in bands other than visible light. Somebody had to discover that. I mean, just think about it. Why would you have any inkling? Why would you believe at all that there was a kind of light out there that your eyes could not detect?
Right.
Especially if you're religious, right? If you're religious, what? God made humans and we have eyeballs to see light. And how could there possibly be something we can't see? All right? So there's certain expectations of who and what we are as a life form that were completely overrun the day infrared light was discovered. Okay? And did I tell you how we discovered infrared? I tell you?
But
it was did we? It was William Herschel discovered it.
Okay, never mind. Tell the story.
Okay, no, real quick.
I was thinking of something else. I'm like, okay, wait a minute.
William Herschel discovered it, and how did he do it? He knew that Isaac Newton figured out that white light is composed of colors. You just pass it through a prism and it breaks it apart. So he repeated this experiment. You put a little slit of light in your room, but the whole room has to be dark so that only the spectrum shows up. All right, and you pass it through a triangle prism. You get a rainbow on your table. And there it is, red, orange, yellow, green, blue, violet. And he had the foresight to ask the question, I wonder if the different colors of light have different temperatures.
Yeah,
just to even ask that question.
It's just pretty impressive question.
Think about that. It's a simple question, maybe retrospectively obvious, but at the time, okay, so what does he do? He has a thermometer and puts it in each of the different colors of light. But wait a minute, you need a control thermometer. So he took his control thermometer, put it off to the side, just to the side of the red. Okay? So that was not in the spectrum. All right? And that would presumably just measure room temperature. All right? But it was still on the table where he was measuring the rest of the temperatures. Your control has to have a minimum of variation other than the one thing you want to change. Okay? So the thermometer's on the table, but just off to the side. And so there he is, he's measuring the temperature of blue and red and yellow. And what he's finding is that the thermometer off to the side is consistently measuring higher temperature than all the rest of the thermometers, all the rest of the readings that he was taking. And he said, WTF? I'm sure that's what he said, okay?
Yes, exactly.
I am sure.
And right after that, he went, OMG!
That's
OMG, W2F!
All right, so he publishes this paper, and it's beautiful in how he's tiptoeing around a discovery because he doesn't really know. He said, could there be light that is unfit for vision?
Unfit for vision.
This is how he described it.
That's a great description.
And he does this enough, and I think I've discovered light unfit for vision. You're damn right you did, and it's light below the red, and what do we call it? Infrared.
Wow.
Okay.
And it's so funny, you still see the hubris of human existence there. It's unfit for vision, not we can't see it.
we blind to this
Right,
thing.
exactly.
It's got the problem.
It's got the problem. Not
It's
us.
unfit for us.
It's unfit for vision.
I hadn't thought about it that way. Very good. Yeah. So it turns out, so that's just an interesting sort of discovery experiment. And then we would learn, well, if that exists, maybe other bands of light exist. And so thus, thereafter, we would discover ultraviolet, microwaves, radio waves, X-rays, and they each have their moment in the sun, so to speak. And that fills out the entire, what we call electromagnetic spectrum. Only a small fraction is visible light. And so now you're going to say, what in the universe gives off infrared light? And you find out that things that have kind of any temperature at all will radiate in the infrared. Okay? Now, so for example, if you have an electric stove and you put it on low and turn out all the lights, can you see it? No. Not if it's on low, but you put your hand on it, you'll burn your hand. Okay? So
Tell me about it.
Something is coming out of the stove and it's not unfit for vision, right? It's infrared light. Okay. And when the thing gets hot enough, it's not only giving off infrared, it'll begin to also give off visible light.
Right.
Okay? But if the thing is cool enough, it's primarily only going to be giving you infrared. Suppose you want to see infrared. All right? And by the way, infrared doesn't make it very nicely through Earth's atmosphere. You know how you know this? Because we have greenhouse gases that trap the infrared that is down here. Okay? Right. So the greenhouse effect are molecules that have a special relationship with infrared. And there's the ground trying to radiate infrared back into space. It said, no, you don't. And it sends it back down and accumulates. Okay. So here's the cool thing about the James Webb Telescope. It has a special reflective surface on its mirrors that are tuned to reflect infrared with very high efficiency. That's number one. Reflect and focus. Number two, if you're trying to detect something that is a very low temperature, what happens if you have a temperature and you're the detector? You end up detecting yourself.
Exactly.
Can't have that.
I went searching for the universe, and all I found was me.
So you need a way to cool the telescope. So we could send up cryogenic liquids and things, but they would eventually evaporate or gain temperature. And so what we figured out to do, not I, the engineers who were tasked with this. That telescope has a series of thermal baffles between it and the sun. All right, and so those, just take a look at any photo of the full telescope deployed. They're basically screened. They're like sheets that are put up, a series of them in the row. So sunlight comes and hits one of them. It reflects some back. Others get absorbed and gets retransmitted to the next sheet, but that gets resent back. There's this multiple, triple reflections, and at each layer, the amount of heat from the sun is dramatically dropped. Okay?
Gotcha.
Dramatic. By the time it comes out the other side, it's barely there at all. And so the temperature of the telescope can now drop to what is basically the temperature of deep space without any influence of sunlight increasing its body temperature, if you will.
That's wild.
It's totally wild. So now the James Webb Space Telescope can observe deep in the infrared part of the spectrum because it can. And so there you have it.
That
A little primer on infrared and infrared telescopes and how that works.
Well, there you go, people. I hope you were paying attention because you're going to be at a cocktail party where this is going to come in very, very handy. I plan on using it this weekend. I'm telling you right now.
It's what's that skirt for on the outer edge of the telescope?
There you go. I suppose you didn't realize that there were baffles that actually filter the sunlight in such a way that cools the telescope so that we're able to register the infrared without registering the heat from the telescope itself. Yes, this is the kind of stuff you learn when you're an extremely smart individual. By the way, off with you. Okay.
That's why you don't have any friends left at your party. Right, Chuck, we've got to take a quick break, but when we come back, more things you thought you knew on StarTalk. So you might have heard intermittently, every now and then, that Earth's poles will flip. Have you ever heard? You've heard that, right?
I've heard people say it.
Say it. Well, thank you for clarifying that, right? And clarifying that it's not what is true, it's what people say or think is true. These are not always the same thing. So it was especially bandied about when we were approaching not only the year 2000, but also the year 2012. About every 10 years, people band together and want to declare that the world is about to end based on some cosmic force. I'm intrigued. I think that people need followers. If you're the one saying the world's going to end and no one else is, people will think you have special knowledge, and then you become sort of this guru of prognostication. So let me just make it clear that Earth's rotation axis with Santa Claus at the top is not flipping. That is a completely stable configuration. We bob up and down a little bit, okay? And so on our spinning axis, we not only precess, which is a fancy word for wobble. Okay, we wobble. If you ever played with a top, as the top slows down, you see it wobble. But also we bob up and down, okay? And they all happen on very different time scales, but none of them involve a flipping of Earth's axis, north and south. However, what does flip are the magnetic poles. The magnetic poles. Now, let me just nip something in the bud here, okay, just so you know. You're old enough to have probably used a compass in your life when you were a kid, all right? Okay, which way does the compass always point?
North is what they say.
Okay, so that's correct. And it points to the North Magnetic Pole, all right?
Right.
Which, by the way, does not exactly align with Santa Claus, all right?
Okay.
By the way, there are things in the universe where it's almost at 90 degrees to each other. So there's nothing specially, it's no cosmic pre-requirement that they perfectly align in the spinning object, all right? So in our case, they don't align. The North Pole is sitting somewhere in northern Canada. All right. So if you're trying to find Santa Claus with a compass and you're in northern Canada, you're going to land in the wrong spot.
Oh, wow. Okay.
Just to be clear about that.
No wonder we can't find them.
That's why you didn't get your presents. You didn't get your presents this year,
That's why he's so good. Yeah.
You didn't get your pony.
Yeah, exactly. I can't find this. You're going to pay what you owe, Santa.
So it'll find the North Magnetic Pole. All right. So that thing that's pointing there is the North Pole of the compass needle. The compass needle is itself a magnet with a north and a south pole. Now here's a little known fact. Okay. What can you tell me about north and south poles of a magnet? Take two magnets together. What do?
Well, they repel each other if it's the same pole.
Which repels? Which repels?
So north to north and south to south.
They each repel each other.
They repel
correct?
each other, right?
The like charges repel.
Right.
So wait a minute. If the needle of a compass that says north on it points to the North Pole, shouldn't it be pointing in the opposite direction?
Right. It should be repelled and pointing down.
Okay, except it's not. It's attracted, which tells you that Earth's south magnetic pole is in the north. Because the north part of all magnets point in that direction.
Okay.
Okay. I don't know if you knew that.
No.
Okay.
Here's the thing. What you did was you took the empirical and put it first.
Yes.
And then you said the ridiculous thing afterwards. So now what am I left to do? I'm like, well, he already proved it. So what am I going to do? Like,
yeah, it's pre-approved.
It's
pre-approved science.
I can't say like, yeah, right, whatever,
Yeah, no, because you already were with me on it.
Exactly.
You
I was
helped
like,
me.
yes, absolutely right.
Demonstrate this. They don't tell you that in the Boy Scouts.
No, they don't.
That the Earth's south magnetic pole is in the north, which is why all north poles of magnets point there.
Sorry, little Tommy, but you're screwed.
No,
your compass is lying to you.
Concept of reality is off by 180 degrees. All right, so here's what happens. We have a magnetic field because our core is fluid. All right, all the heavy stuff when Earth was molten, the heavy stuff fell to the middle, and the heavy stuff is the iron, and the light stuff, which is the rocks, floated to the top. Okay. And we don't think of rocks as light, but it's much lighter than metal, all right? And so nearly all the metals went to the core. Some got frozen in place, as we have these ores, these veins of ores. As Earth is solidifying, it didn't fall down fast enough, and it got frozen in place. There are other occasions where volcanoes can redistribute material from below and put it up in the crust. But basically, most of Earth's iron is in our core. And it's hot. And so the iron is molten. And when you have molten and you're spinning, you have moving magnetically chargeable metals. Okay? Iron is magnetizable. When you have moving metal, you create what's called a dynamo. And in a dynamo, you basically create a magnetic field from scratch.
Wow.
That's why old dead planets that have cooled do not have magnetic fields.
Right. Wow.
Okay. They don't have magnetic fields. Like Mars, no magnetic field to speak of. Okay, because it's cooled faster than Earth did. It's smaller, so if you're smaller, you will cool faster. And so no, you don't have this churning. By the way, Mars once did, for sure. Mars has the largest known volcano in the solar system. Okay, so Mars used to be hot on the inside. But that's called Olympus Mons. All right, it makes our volcanoes look like molehills. By the way, it's huge. It's huge. So, anyhow, the point I'm getting at here is the dynamo goes through cycles.
Okay.
And it goes stronger, then it goes weaker, and it flips.
Gotcha.
And so every 500,000 years or so, the magnetic field of Earth has flipped. Period.
Okay. That's pretty wild.
Okay. Yeah, it's fascinating. And while it's flipping, it actually goes to zero and then recovers coming out the other side.
Okay, so then that makes me ask, what does the magnetic field of Earth do for Earth and do for us?
Other than give compasses a meaning in
Yeah,
life.
yeah. Other than confused Boy Scouts who don't understand that the compass should be pointing in the opposite direction.
Well, Einstein was quite intrigued by a compass, that some mysterious force that you can't see, touch, smell, or taste is forcing the needle to move. Right. He was very intrigued by that as a child. So I think we'd be thankful that we had compasses back. If it was just GPS with a handheld device finding north, I think maybe Einstein would not, he might have gone on to play basketball or something. Who knows?
Wow.
Who knows what career he might have had. So, actually, that's the opposite of a Gary Larson comic. That's where I got that idea from. There's a picture of Einstein on a basketball court, and he's like dribbling, right? And it said Albert Einstein in school was destined to be all-star basketball player until an ankle injury sent him into his physics books.
That's funny.
So the point is that the magnetic field has flipped. And what the magnetic field does when it's operating is it creates a magnetic shield around Earth, if you will. And when charged particles come from the sun, the solar wind, we call it, they see this magnetic field and they spiral down towards the poles. Or towards the magnetic poles. And as they spiral down, they careen into air molecules. And if you have two molecules that collide with each other, energy gets exchanged. Okay, so your energy of motion gets boosted into the energy inside the molecule itself. So you've excited the molecule. And then on its own timetable, like fractions of a second, it de-excites and then radiates visible light. So wait a minute, what is that? Oh, I know what that is. That's the aurora.
That's pretty wild.
The aurora borealis, that's in the north. And take a gander what it's called in the south.
Let me see. The southern aurora borealis.
Okay, thank you, Chuck. I'm okay with that. Yeah. No, it's the aurora australis.
The aurora australis.
Australis, right.
Okay.
Because it's symmetric, right?
Yeah,
we have a north pole and a south pole. So we make a big deal of our own aurora because 90% of the human population of the world lives north of the equator.
Right.
So we get aurora. There it is. And we know the field is flipped. You know why? Because you can see volcanic plains where iron came out, and the iron aligned with the magnetic field when it froze in place. And you compare this from different generations of volcanic eruptions, and you can see the flipping of the orientation of the iron particles.
That is
it's remarkable.
That is really outstanding. That's pretty wild because it's a magnet. So it's metal in a magnet, and it's actually
it's doing its thing,
succumbing to the properties of magnetism.
Correct. And if Earth is helping that out, it's going to align them when it freezes out of the volcanic flow. So it's pretty cool stuff, and it all comes together. And by the way, this involved like astrophysicists and geologists, and there was a worry if we don't have a magnetic field, that means the charged particles come straight into us and don't get directed to the poles. Would that be bad for life on Earth? So it might be. You might think it would be, but there are no particularly striking extinction episodes.
Right.
At the times when these
when it flips
magnetic
and it
fields
goes
have flipped.
to zero.
Yeah, there's no. By the way, animals are going extinct all the time, especially now because humans have their hand in this process.
Yeah,
It's the sixth extinction, really.
Wow.
All right. That's in case you didn't know that your compass points south.
That's great.
All right. This has been StarTalk. Things you thought you knew. Neil deGrasse Tyson, keep looking up.